Hi everybody. As promised, this episode's going to be about polyprotic chemicals, and when you're talking about the description polyprotic, it's really referring to both acid and base, and what it's referring to is poly obviously means more than one. Protic refers to the fact that it's proton, and since acids have been defined as a chemical that can donate a proton. If you are polyprotic as an acid, that means you can donate more than one proton. And as a base, bases are defined as accepting a proton, and so therefore if you're polyprotic as a base, that means you can accept more than one proton. So these chemicals are they're unique in the fact that they have more than one to donate or more than one place for to accept. But from a practical perspective, when you dissolve them into water and you create solutions that are acidic or basic, the fact that they are polyprotic does not necessarily mean they have that much more, they pack that much more of a punch. When it comes to the ability to make something acidic or basic. And that's what is kind of unique about polyprotic species, is that you might think they do more because they can accept or donate more, but in reality they don't. That's what this episode is about. This episode is about what are these polyprotic species doing when you dissolve them into water, what's actually there, but then from a practical perspective, what does that mean for the pH of those solutions? And so we'll get into that concept by the end of this video. So the first thing that I've got up here in my list of things that I want to cover, the definition of polyprotic. So I've already kind of defined it already, but in terms of a formula, how are you recognizing that you've got a polyprotic chemical? So if you're talking about acids, so if I were to write down kind of a generic formula for a polyprotic acid, you're going to find one that has H2A, or sometimes you use X, right? So H2A, now that could also be H3A, etc., etc., etc. Also, don't be surprised if your polyprotic species will be an ion. So something like dihydrogen citrate has a charge of negative. It has a charge of -1, but it has a formula that has two H's, two donatable H's. So it is a polyprotic acid, but it's got a negative charge. Okay, so don't be surprised. So all you're looking for are those multiple H's. If you're looking at a crazy organic molecule, chances are you're not going to come across a whole heck of a lot of them in Chem 12. But later on, maybe you'll come across some. You might see a formula that has some kind of R standing for some organic chain of carbons. And then you might see something like COOH inside of brackets with a subscript of 2, meaning there's 2 carboxylic acid groups on this molecule somewhere. And when you start getting into like pharmaceuticals and different types of medicines that are out there, oftentimes organic compounds, they can have 2, 3, 4 acid groups on them because they're very big molecules oftentimes. And so they have multiple points of being able to donate an H. So that's what you're looking for when you're talking about polyprotic acids. When you're talking about polyprotic bases, again, what you're looking for is you're looking for multiple spots to be able to put a hydrogen, right? And so multiple spots where you're looking to put a hydrogen oftentimes means that you're looking for a chemical that has a negative charge of -2 or lower. So you're looking for something like, and I'm going to switch over to X. So X to the charge of -2, X to the charge of -3. Okay, so a negatively charged anion sorry, that's redundant. So an anion with a charge of -2 or lower. Again, don't be surprised if you come across something that maybe has an H attached to it. Give you an example. Monohydrogen phosphate, so HPO4, has a charge of -2. Well, I guess technically that is a polyprotic base. Because it has a charge of -2, you can put 2 H's onto that. There's room for 2 more H's to go back onto it. Doesn't necessarily mean that that's what it's going to do, but there are 2 spots for it. Now, an unusual one that you might come across is you might come across, say, an amine or an amino group that has a -1 charge. And so I'll just write the one down that kind of strikes me right off the bat. If I had NH2 with a charge of -1, well, if I add 1 H onto that, it goes to NH3. But the nitrogen still has a lone pair of electrons, and if you remember back last episode with the weak bases, if you have a lone pair of electrons, the lone pair of electrons acts as a docking spot for an H+. And so if you do have a nitrogen in particular that has 3 chemical covalent bonds bonding to 3 different things, then there's still a spot for a hydrogen even though it doesn't have a negative charge. So in this case, the -1 charge of NH2 negative, an H can fill that negative charge to bring it to NH3, but the nitrogen still has a lone pair of electrons, so you could add a second hydrogen onto there to make an NH4 + 1. Okay, so a little bit of a tricky one. I'm not sure you're ever going to come across that one in any great sense, certainly not in Chem 12. You might get a tricky question, maybe a multiple choice question along the way, but that's about it. So that's kind of what we're looking for, and so you can take the generalized formulas of what these things would look like, and then you can try and apply them to actual real molecules. So the second thing that's up here on the board is strengths of successive stages. So I want to use 2 examples, and I've got them on the board behind me here. So to demonstrate this point, that when you're talking about a polyprotic species, more often than not, because they've got more than 1 H, people will oftentimes come up with kind of weird and wonderful formulas. Because it's got 2 H's, it might donate both at the same time. So I'll give you an example. I will show you a mistake. I'm going to, 1, qualify that it's a mistake. So don't copy this down. I'm going to erase it right away. But this is what I've seen in the past, is that something like H2, well, I'll use, there's oxalic acid. And students in the past have made the mistake of saying, well, it's got 2 H's. Therefore, it can react with 2 water molecules. Whoops. Oh, my goodness. Let's just start that one again. And form 2 hydroniums plus C2O4 -2. People will write that incorrectly. That equilibrium that's there, and let me explain why it's incorrect before I erase it and try and erase it from your brain. The reason why that is incorrect is that equation makes the assumption that both of these hydrogens right here come off with equal ease. Okay, so they get donated with equal amounts of force, I guess. But this is kind of what happens, and I want you to think about this one logically. When the first H falls off of it, okay, so let's pretend H2C2O4 bumps into a water molecule and donates its H. The first H comes off, okay, whatever. Now it's got 1 more H to fall off. It's not going to get rid of them simultaneously. So it gets rid of the first one. Now it has a negative charge. And just logically, if a chemical has a negative charge and it's trying to unload a +1 onto somewhere else, well, the fact that it's got a negative charge means it's resisting getting rid of a positive charge. It's going to want to hang on to it because it's already negatively charged. It's attracted to it. Let's keep it simple. So The second hydrogen does not come off as easily as the first one comes off. And that is a consistent theme in all acids and all bases when you're kind of looking at it the other way around. The first hydrogen is always easier than the second, which will be easier than the third, which will be easier than the fourth, so on, so on, and so forth. So when it says up here, strengths of successive stages, what I'm talking about is that the first H comes off easier than the second, and the second comes off easier than the third. So what you have to be thinking about is you have to be thinking about polyprotic acids and bases as actually reacting in successive stages. And so you can't think of this because the two H's to form hydronium are not coming off as easily. Okay, so let me show you what I mean. So let's start with the oxalic acid. So we throw an oxalic acid into water, and so there it is, forms a molecular solution plus a single water molecule. And I've tried to throughout this time, and I've said it multiple times, where a Bronsted-Lowry acid-base reaction is the transfer of a single proton. Two chemicals bump into each other. The acid donates one hydrogen to the base. That's it. Not two, not three, not four, one. And so that one hydrogen goes from the oxalic acid over to the water molecule, making a hydronium. Whoops. And HC2O4. Sorry, I kind of squished that one in there. I want to leave a little space there. You'll see in a sec. So one hydrogen gets transferred over to the water. Looking at my Ka table. Okay, so again, this thing's kind of critical. I look at oxalic acid, and where is oxalic acid on here? It's up near, like as weak acids go, oxalic's actually pretty good. So oxalic acid has a Ka of 5.9 times 10 to the negative 2. So Ka, 5.9 times 10 to the negative 2. So it's not bad. As weak acids go, it's not bad. So that is, think of the Ka as something's ability, I guess proportionally, its ability to get rid of an H, one H, onto a water molecule. Now, this thing right here, okay, which is called monohydrogen or binoxalate, monohydrogen oxalate is more the modern form. So this hydrogen oxalate that is produced in that first stage, meaning one H is eliminated from the oxalic acid, that thing in its own right has a hydrogen, which means that this thing could continue on. So it's made in water, and as soon as it gets made in water and floats around, well, it's going to bump into water molecules as well. When it bumps into a water molecule, it has a hydrogen to donate, and sure enough, it could donate it. Now, regardless of well, it could also, it's got a negative charge, it could be a base. Well, we're talking about this oxalic acid, the original chemical, acting as an acid. So we're going to kind of stay in that genre of it, producing hydronium ions. So this thing, some of those ions floating around bump into water, they make another hydronium, because they donate. Plus C2O4 negative 2. Now, if you combine those two, sure, you get an oxalic, two waters, two hydroniums, and this hydrogen oxalate cancels. So overall, sure, you could make that argument that they have a net reaction of two hydroniums being made. However, take a look at the Ka of the hydrogen oxalate. So hydrogen oxalate is down here. It's further down the table. So oxalic acid was up there. Hydrogen oxalate, I lost it now. Where did it go? Hydrogen oxalate, there we are. Hydrogen oxalate, right where my thumb is there, that has a Ka of 6.4 times 10 to the negative 5. So it's about 10 to the negative 2 versus 10 to the negative 5. It's about 1,000 times weaker than the original acid. So this guy is about 1,000 times weaker than H2C2O4. Now, that's a significant thing because whatever is produced in this first stage up there is dependent upon the value of this Ka, the 10 to the negative 2. Whatever is produced in the second stage has to do with this Ka, right? Not the first stage. The first stage is kind of done by the time this thing's going on. And it's 1,000 times weaker. So what can you say about the hydronium that's made in that second stage versus the first stage? Well, I guess in theory, you just kind of keep the relative amounts here. It's about 1,000 times less than the first stage because the Ka is about 1,000 times lower. So that means that, okay, the second stage happens. Okay, I will not deny you that this second stage happens. But the amount of hydronium that it makes is way, 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 way smaller than what the first stage made. In other words, it's insignificant relative to the first stage. So if I was doing a calculation using oxalic acid, I would go ahead and I would do this. I would use this equilibrium equation right here. It's weak, so I would do an IRE. I would fill in my IRE, and I would use my K expression for oxalic acid for this equilibrium. I kind of erased that with my hand. I would use the stage 1 K expression. I would calculate the hydronium from stage 1. I would ignore stage 2. It's happening, but it is really insignificant compared to stage 1. So I can ignore the number of hydroniums produced from it. It is happening, but they're insignificant. So if someone ever asks you, well, what's the pH of the solution? You use that equilibrium to calculate the hydronium and the pH. You can ignore the second stage because it's insignificant. If somebody ever asks you, if you have a solution of oxalic acid, what ions are present, then you would say, okay, so the reality is, if someone just asks you what things are present, well, this is an equilibrium, so it goes both ways. So this guy's present, this guy's obviously present, this guy is present, and then in the second one, the second stage, although insignificant mathematically, still happening. Which means, well, I've already counted that. This guy is also there. So all 4 of those are floating around in the water. So it's really important that you get kind of what is happening in reality, but mathematically what things are significant. And so if I was doing pH calculations with a polyprotic, the first stage is all that really matters. The second stage doesn't actually matter mathematically. Now, there's one situation out of the thousands of situations you might have. You may have a solution of sulfuric acid. Now, I'm not going to go through this one. I'm just going to say it to you, that you might actually have to calculate for the second stage. In which case, you look at your table here, and sulfuric acid is right here, H2SO4. H2SO4 is a strong acid. So the first stage of sulfuric acid is not in equilibrium, it's 100%. And so the hydronium from the first stage equals whatever the sulfuric acid concentration was. The second stage, HSO4 minus, is actually, from a weak acid perspective, where is it? It's still really quite high up here on the table. So HSO4 minus, which would be the stage 2 acid, may in fact produce a significant amount of hydronium compared to stage 1. So you have to actually go ahead and calculate that number to see how much actually the second stage made. Now, I'm not going through that because oftentimes people don't ask you that question, but if they did, you might have to do the stage 2, add it, use your sig fig rules to stage 1 and see, did it actually make a difference? Does it actually contribute significantly to stage 1? So you'll do that if you'll cross that bridge if you actually get to that situation. So that's the acid. The base is very, very similar. So I'm going to flip this around. So I'll erase it first. And so polyprotic bases, for example, the phosphate ion. Okay, so what is the phosphate ion? So the stage 1 would be PO4 negative 3. That's phosphate. So if you have a solution of phosphate, phosphate reacts with water. And although the phosphate has a charge of negative 3, a Bronsted-Lowry acid-base reaction is the transfer of 1 proton. So the PO4 minus 3 accepts 1 hydrogen from a water molecule to make HPO4 negative 2. So if it started negative 3 and you add a plus 1 on a number line, negative 3 up to plus 1 goes to negative 2. So that's the charge of monohydrogen phosphate plus hydroxide. Now, because this is a base, then I wouldn't have a list number here for the Ka's. I would have a number down here for the KB's. Now, the KB's are not on the table, so I'll quickly do that calculation where you take the KB of a base equals KW divided by the Ka of the conjugate acid. So the Kb of this chemical is Kw divided by the Kb of PO4 minus 3 is equal to Kw divided by the Ka of that compound there, or that ion. So I will do that on my calculator. So 1 exponent negative 14 divided by, and then I look up HPO4, and it's way down on the table. Like HPO4 is way down here. There's PO4 over on the base side. So it's actually a pretty good base. PO4 is pretty nasty stuff. So the Ka is 2.2 times 10 to the negative 13. So divided by 2.2 times 10 to the negative 13. And so this guy comes out to 4.5 times 10 to the negative 2. So that's stage 1. Okay, stage 2. Okay, so what's the stage 2 base for this thing? Well, you take whatever was made in stage 1 and you kind of bring it over here as now the base for stage 2. I'm losing a little bit of room, so I'm not going to put any of the subscripts, the aqueous liquid. We know it's aqueous liquid, aqueous, aqueous. So let's just move on here. So plus water in equilibrium with, okay, picks up another H from a water molecule, making H2 PO4 negative 1. We're now up to negative 1 plus hydroxide. Kb of that guy, okay, so I'm taking Kw, the Kb of this guy equals Kw divided by the Ka of its conjugate, H2PO4. So now I'm looking on the periodic, or on the Ka table, I'm looking for H2PO4, which is now a little higher. Okay, so the base, HPO4 minus 2 on the other side, is weaker than the PO4 was. So there's PO4, there's HPO4 up there. Okay, so the base is getting higher on the table, meaning it's getting worse and worse and worse and worse as a base. So what is its value of Kw? So we're taking, or its value of Kb, sorry, I missaid that, misspoke. 1 times 10 to the negative 14 divided by, and H2PO4, 6.2 times 10 to the negative 8. And that is 1.6 times 10. 1, 2, 3, 4, 5, 6, 7 to the negative 7. So it plays out in the KBs. So the first stage was 10 to the negative 2. Second stage is 10 to the negative 7. Okay, so the third stage then would be this. It's got a third stage. How do I know it's got a third stage? Well, it still has a negative charge. H2PO4 is still a negative 1 charge. So there's still room for a third H. So you know how many stages there are based on what the charge of the original base was. Negative 3, you're going to have 3 stages. Negative 2, 2 stages. Negative 5, 5 stages. So this third stage will be H2PO4 minus this guy plus water in equilibrium with. Now you take another H off of water, put it onto the H2PO4, and you get H3PO4. Now you're up to neutral, so that's where it's going to finish. Like there's no more room, and it's not a nitrogen compound. Plus hydroxide. Now this guy's Kb is 1 times 10 to the negative 14 divided by, so now I'm way up here where H3PO4 is now. That's the conjugate acid. So that's 7.5 times 10 to the negative 3. And I get 1.3 times 10 to the negative 12. So you can see that each stage, the actual base that's involved in each stage is getting weaker and weaker and weaker, right? So from there to there is approximately 100,000 times, because that's 10 to the 5th, about 100,000 times weaker. Then again, it's about another 100,000 times weaker. So every stage is producing less and less and less and less hydroxide relative to that very first stage. So mathematically, if someone said, calculate the pH of a 2 molar solution of PO4 minus 3. Well, the only significant stage for calculating the hydroxide of this base will be this one. So you would do an IRE table for that equation. You'd do a K expression for that equation. You'd fill it in for that equation. You'd use that Ka, that 10 to the negative 2, Kb, sorry, and you'd calculate hydroxide. The second stage will happen. This is going to happen, but it's making such an insignificant amount of hydroxide it doesn't even do anything to the first stage. I guess maybe you could mention the second and third stage produce insignificant hydroxide, and that kind of explains why you're not considering them. But you have to get in your own mind. Like, this is something that you have to understand, that this stage happens, but insignificant hydroxide. The third stage even happens, but it's insignificant hydroxide. Okay, so that's kind of the gist of it all. Polyprotic species, they happen in stages, and the first stage is typically the only one that matters from a pH perspective. Second, third, fourth stages happen, but they are insignificant when you're doing any kind of mathematical calculations. Okay, next class, we're going to be talking about an amphiprotic chemical, or amphiprotic chemicals, not one, there's multiples out there. So an amphiprotic, just to kind of give you a little bit of a heads up, amphiprotic chemicals are those that can act either as a base or an acid. And so there are certain clues that they have that they can either be an acid or a base. So we'll look at those different things, and then we'll kind of lead into, well, how do you know what it's going to be? Okay, and so it's just a comparative thing, because if they can be an acid and a base, they'll have a Ka and a Kb. So we'll get into how we figure all that stuff out. So hopefully that was helpful in terms of polyprotics. Some teachers don't even bother kind of going into the math of polyprotics, so you may or may not be covering this, but in case you do, hopefully this was helpful. As you're going along, if you haven't been kind of contacting some of the people that are in your class, or friends that you know, or anything, or colleagues that you have, that if you're finding these things helpful, make sure you're sharing this series of videos, because maybe they can pass it on to other people even if they're not using it. Maybe subscribe to the channel, so every time I make a new video, you'll get a notification for it. And the more I can kind of get people connecting to this thing, maybe the more helpful it can be. Okay, so feel free to share and subscribe and embed the link into your own websites, or download them onto your own computer and use them as you see fit. So hopefully it's been useful, and next time we'll see you for amphiprotics. Okay, see you later.